Okay, good morning everyone. So today we're going to try something a little bit different for our math lecture. As you know, I couldn't make it to Dauphin. We're going to continue on. I will review your test with you next week, but for right now we're going to begin chapter 12 on exponential functions. We were slated to do some trigonometry next, but I think it will be easier to explain this type of thing through a video, so we're going to go on to the log and exponential functions, and then after that we'll continue back. We'll go back to the more trig. So chapter 12 is on exponential functions, logarithmic functions. Today we're just going to go through 12.1. There's quite a bit of information there, so I want to make sure we really drive this home, and I will give you a short assignment based on 12.1 that you can work on in the next week. So, an exponential function, basically what we are saying here is when we've talked before about exponential expressions with rational number exponents. So if you have 8 to the 1 over 4, 3 to the negative 3 over 4, 7 to the 2.34, so we've talked about all these different kinds of exponential expressions that have rational number exponents, but we haven't really talked much about exponential expressions with irrational exponents. So we know that taking the square root of any number that isn't a perfect square is going to give us an irrational number, so something like the square root of 3 or the square root of 5. So now we need to turn our attention to talking about those types of numbers as exponents. So your textbook gives the example, and this is all beginning on page 864, so you should definitely follow along. The textbook gives the example of 5 to the square root of 3. So because we know how to approximate irrational numbers with decimal approximations, for example, we know that the square root of 3, because it's between the square root of 1 and the square root of 4, and those numbers are 1 and 2, then we know that the square root of 3 must be a number between 1 and 2, and we're able to kind of close in closer and closer on what the actual value might be. So because we're able to do that, we can then approximate what 5 to the square root of 3 would be. So for example, if we know that the square root of 3 is going to be between 1 and 2, then we know that the expression is basically saying that it's either 5, it's somewhere between 5 to the 1 and 5 to the 2. So I'll show you a little bit of what I mean, and I'm going to be basically showing you this PowerPoint slide, but then also going back and forth and showing you examples as I've written them out, so hopefully this works properly. So for example, you can see right here on the top of the page that we have 5 to the square root of 3, and so we know square root of 3 is in between 1 and 2. As we close in on the root 3, we're going to get closer to the specific answer. So we know not only is it between 1 and 2, we know it's between 1 and 7. It's also between 1.73 and 1.74, so we're getting more and more specific. And finally, we know it must be between 1.732 and 1.733. And like I said, conversely, if we know that the root 3 is between 1 and 2, then we know that 5 to the root 3 must be between 5 to the 1, which is 5, and 5 to the 2, which is 25. So the number we're looking for is somewhere between 5 and 25. So we can also narrow it down that way. So what you end up getting overall is, because like I said, we narrowed that root of 3 down to somewhere between 1.732 and 1.733, then we know that our number must be between 5 to the 1.732 and 5 to the 1.733, which is somewhere between 16.241 and 16.267. So basically we're able to estimate it there. So to 7 decimal places, we end up getting that 5 to the root 3 is somewhere around, and like we said with the rational numbers, they go on forever and never repeat. But it's approximately 16.2424508, and you can see that in your textbook. So, based on this, we've learned that any positive irrational exponent can be defined in a similar way, and that negative irrational exponents are defined in the same way as negative integer exponents. So we know whenever we have a negative integer exponent, for example 5 to the negative 2, then it's the same as saying 1 over 5 to the 2. So the same thing happens with negative irrational exponents. If you had 5 to the negative root 3, it's the same thing as 5 to the root 3, but you have to do 1 over 5 to the root 3 instead. So it's still going to be the same answer, it's just going to be 1 over that answer. So now we move on to define what an exponential function actually is. That was just kind of an introduction into how we can help estimate these types of irrational exponents. But an exponential function in general is any function f of x is equal to a to the x, where a is a positive constant different from 1, so a cannot be 1, and the base is then called a. So whatever you're raising to the exponent is called a. The reason that we say that the base, or the a value, must be positive is that we want to avoid the possibility of taking an even square root of a negative number. Because as you know, we can't take an even square root of a negative number. So for example, if you let a be negative and a was a negative 1, then if your x value is 1 to the 2, which as we know, raising something to 1 to the 2 is the same as taking the square root of it, you cannot take the square root of negative 1. It's not a real number. So in order to maintain all of our numbers being real numbers, we want to always limit our a value to being positive. So the first example we're going to run through is graphing the exponential function f of x is equal to 2 to the x. So as we've talked about many times, basically when you get an equation like this, f of x is equal to something and there's an x involved, you're just going to plug in values for x and then you're going to graph based on that. So as your textbook has, I have plugged in 0, 1, 2, 3, negative 1, negative 2, and negative 3. So hopefully you can see my little example here. So you find that when you have your f to the 0, you end up getting 2 to the 0, which is 1. F of 1 is 2 to the 1, which is 2. F of 2 is 2 to the 2, which is 4. F of 3 is 2 to the 3, which is 8. F of negative 1 is 2 to the negative 1, which is 1 over 2 to the 1, or 1 over 2. F of negative 2 is going to give you 2 to the negative 2, which is going to be 1 over 2 to the 2. Like we said, that's what happens with a negative exponent. You just put them 1 over the number, which is 1 over 4. And f to the negative 3 is 2 to the negative 3. F of negative 3, sorry, is 2 to the negative 3, which is 1 over 2 to the 3, which is 1 over 8. So getting those values, then you're going to plot them on a graph. So I haven't listed out the table of values then with the x and y values. Your book has done that for all of these examples, so I figured it wasn't really necessary for me to do that as well. Just going to try to move this a little bit so I can see better what I'm pointing at. But what you're going to find it looking like if you plot it with a smooth curve is something like this. You're going to start out very small, and as you increase, you're going to get bigger and bigger, because obviously, as we know, if you're raising 2 to exponent, it starts out small. You know, you have 2 to the 1, which is 2, and 2 to the 2, which is 4, but then you get 2 to the 3, which is 8, and then 16, and it gets bigger very, very quickly. So you see the curve starting very small, especially when you get past that y-axis in the negative x direction, and you end up getting those very small values. But you are going to see the curve start to increase very, very quickly. So something that you might notice here is that x gets very small, and you'll see the curve starts to come very, very close to the x-axis, but it never touches it. So in this case, the x-axis is what we call an asymptote. Basically, that means that it's the line of which this graph will never cross. It will get very, very small, but it will never cross that x-axis because y is never going to be a negative number. So your x-axis, or your y to the 0, is the asymptote for this graph. So in graphing, there's a couple points to keep in mind, and these are listed at the bottom of page 865. In graphing, you want to be sure to plot enough points to determine how steeply the curve rises. So you want to really be able to see that actual quick ascent of the graph, so where it's going up very quickly. You don't want to just plot, for example, you know, -2, -1, and 1, because you wouldn't really get to see how quickly the graph is going up. You want to go to at least 3 or 4 in this case. And like I said, the curve does come very close to that x-axis, but it will never touch or cross it, so that's the second point to keep in mind. And another thing to note, as listed in your book, as the x increases, the function's values increase indefinitely. So you do see it going up and up upwards basically towards infinity. But then, of course, as the x decreases, the function value decreases and get very close to 0. So because they're getting closer and closer to 0, because you're getting, 1/4 and then 1/8 and 1/16 and 1/32, and it's getting very, very small, but it's never going to actually cross that 0. It's never going to become less than 0. So basically, your starting point is going to be that 0, and then you're continuing on up into infinity. So for example 2, we're going to try a little bit of a different graph. So instead of doing the graph of 2 to the x, we are going to try the graph of 1/2 to the x, which should give us a little bit of a different graph. So it's important to keep in mind, and you'll see this here in my notes, when you start to do this one, you might notice that the graph of 1/2 x, well, 1/2 is the same as saying 2 to the negative 1, like we just talked about. If you had 2 to the negative 1, that would be 1/2 to the 1, which is 1/2. So in that respect, we can say that instead of saying 1/2 to the x and having to use that half, we can just say that it's the same as 2 to the negative 1 to the x, which is the same as 2 to the negative x. So we'll do it that way just to make it a bit easier for our calculations. So again, we pick our values for x and we plug them in. So we're going to do again 0, 1, 2, 3, -1, -2, -3. So for our 2 to the negative 0, well, obviously anything to the 0 is just 1. If you do 2 to the negative 1, that's the same as saying 1/2, which is 2 to the 1, which is 1/2. If you plug in a 2, you get 2 to the negative 2, which is the same as saying 1/2 to the 2, which is 1/4. If you plug in a 3, you end up getting 2 to the negative 3, which is the same as saying 1/2 to the 3, which is the same as 1/8, and so on and so forth. So you end up getting, when you start plugging your negative numbers in, then of course because you already had a negative exponent, it turns back to positive. So that's when you start to get your 2 to the 1, 2 to the 2, and 2 to the 3. So you notice we got the same values as we did last time. We still have our 1, our 1, our half, our quarter, our eighth, our 2, our 4, and our 8 as our values, but it's going to make a little bit of a different graph. And so we'll see now how that affects what the graph looks like. So if you look right here at the graph, and I did include the table of values this time, basically you've got the same values, it's going in a different direction, so you get the same exact shape, it's the same type of curve, it goes very close to the x-axis but never touches, and then it goes up to infinity, but you'll see that it's reversed. So basically it's a reflection across the y-axis of the first graph, because basically even the y-intercept is the same, you're still getting that y-intercept at at y=1 there, but it's just that the shape, instead of going up like this, it's going up like this. So it's literally been just kind of reflected across that middle y-axis. These properties are very important because, like we talked about with quadratic graphs, you need to know how plugging certain values in certain parts of the equation will change the shape of the graph. You're always going to get that same general shape, but it might be manipulated in ways. It might be steeper, it might be less steep, it might be flipped, it might be moved up or down. So we're going to go through all that just like we did with the quadratic graph. And so basically these examples that we've seen so far do illustrate some characteristics of exponential functions with different bases. Again, keeping in mind that our base, so our a value, if we're saying f of x equals a to the x, must be positive and it must be different than 1. So we found by looking at these graphs that when a is greater than 1, such as in the example where it was 2 to the x just then, we see that the function increases from the left to the right. So we see it kind of starting small over on the left and increasing to the right. The greater the value of a is, so if a was 3 instead, so if it was 3 to the x, the steeper the curve is going to be. So obviously if you think about it logically, if we had 2 to the 1 and 2 to the 2 and 2 to the 3, and instead you replace that with 3 to the 1 and 3 to the 2 and 3 to the 3, well, those are going to be much bigger numbers and they're going to increase a lot more quickly. Instead of having your 2, your 4, and your 8, you're going to end up having your 3, your 9, and your 27. So it's going to increase a lot faster. So therefore the curve is going to become steeper. And as x gets smaller and smaller, like we see in our little graph here, as it gets smaller and smaller, the curve gets closer to the line y is equal to 0, the asymptote. So it's always going to get closer to this x-axis. On the other hand, when your a is less than 1 but still greater than 0, because like we said, a cannot be less than 0 because that would be a negative number, the function f of x to a to the x decreases from left to right. So like you saw in the second graph. So instead of increasing from left to right and going up like this, it decreases from left to right. So it's actually increasing from right to left, if you want to talk about it that way. And as your a value approaches 1, so as it gets closer to that 1 value, the curve becomes less steep. As it gets larger and larger, the curve gets slower, or sorry, it's supposed to say closer to the line y is equal to 0, which is the asymptote, or the x-axis. So just like we said with that one, if you had a 3 to the x instead of a 2 to the x, it's going to get steeper and steeper. In the same way, if you have a 1 over 3 to the x instead of a 1 over 2 to the x, it's going to get steeper and steeper. So actually, as it gets closer to 0, the curve gets steeper and steeper in that case. So it's a little bit different in that way. And you can see those just by looking at the graphs. And I have drawn you just a couple of rough graphs here to kind of illustrate what that might look like. So the first over here, if you had our first graph that we made, the g of x or f of x equals 2 to the x, you'll see the curve is kind of slight like this. But if you had something like 3 to the x, you're going to get a steeper curve. So it's going to start out and it's going to go up much more rapidly. Whereas if you had your 1/2 to the x, like we just did for the second graph, you're going to have kind of a slower curve. It's still going up in that left direction. But if you had something like 1 over 3 to the x, it's going to increase much faster, because like we said, that's basically the same as saying 3 to the minus x then. So it's going to get bigger, the values are going to get bigger much, much quicker, and so you're going to be getting that steeper slope in your graph. So, we need to talk about the y-intercepts. I kind of mentioned them earlier, but you might notice in both of those graphs, if you look at where the y-intercept is, you're going to see that it's at -1 in both of the graphs. Or sorry, I keep saying negative. It's at +1 in both of the graphs. So it's a +1 here, and you'll see that if you look at when f is 0, if you take the f of 0, you're going to get 1. But in our second graph, if you take f of 0, you're also going to get 1. So if you have something in that form where it's just an a raised to an x, your y-intercept is always going to be 1. So it's always going to be 0.0 and 1. So the y-intercept of exponential function, if you have any function that's f of x equals a to the x, so there's no other kind of transformation or translation to it, you are going to see it going through that point, that 0 and 1. That will always be the y-intercept. So you might remember when we were doing quadratics in the last chapter that there were many translations that could occur. So if you had in your formula, you had, x minus something, then you were going to move your value so many steps to the right or to the left. You're going to move your whole graph. It basically translates the whole graph over. Or if you had, that k value on the end, so you had +2 on the end, you were going to, move it up to, or if you had -2, you were going to move it down to. The same kind of concept applies to graphs of exponential functions as well. So if you look at something like f of x is equal to 2 to the x minus 2, basically what you're going to see then is you're changing your exponent. Instead of your exponent just simply being x, your x minus 2 is now going to be your exponent. So you have to keep that in mind. You can plug in your values just like you would for the other one. So if you plug in a 0 there, because x minus 2 is your exponent, you're going to get 2 to the 0 minus 2, which is 2 to the minus 2, or 1 over 4. If you plug in a 1, you're going to get 2 to the 1 minus 2, which is going to give you 2 to the minus 1, which is going to give you 1/2. If you plug in a 2, you're going to get 2 to the 2 minus 2, which is going to give you 2 to the 0, which is going to give you 1. So already you can see that things are changing a little bit here. Right now, usually you end up having your 1 value for y when your x is 0, but obviously it's changed here, so your y-intercept is going to change for this graph. And so on and so forth. You keep plugging in your values for your x, and you end up getting for f of 3, you get y is 2, f of 4, y is 4, f of -1, y is 1 over 8, and f of negative 2, y is 1 over 16. So very different values than you were seeing in the first graphs. So if you look at the graph that we end up getting from these, and I've got the table of values there as well, you'll see that instead of our y-intercept being 1 now, our y-intercept, so where our x is equal to 0, is actually going to be at 1/4. So by adding or subtracting something in that exponent, we have actually changed our y-intercept from that typical value of 1. So you end up getting the same shape overall. It's the same type of curve as 2 to the x, but it is translated 2 units to the right. So the whole graph has actually been shifted 2 units to the right. So just as when you have that formula and you have the x minus h to to x minus h squared in your quadratic formula, and whatever h is going to tell you how many places you're moving it back or forth. This is the same thing happening here. If you have something added or subtracted within your exponent, it's going to tell you how many blocks your graph is going to shift one way or the other, to the left or the right. So you have the same asymptote. That's important to note. You still have that x-axis, or the y equals 0 line, as your asymptote. It's never going to reach that line, but you have a different y-intercept. So now instead of being 1, your y-intercept is going to be 0 and 1 over 4. And there's another type of translation, just as there were 2 in the quadratics, where 1 would bring your graph left or right and 1 would bring it up or down. We have the kind of translation that occurs in example 4, when you have something subtracted or added to that exponential variable, to that exponential function. So instead of changing the exponent this time, the exponent is still x, you are adding or subtracting a number once you've already computed that exponent. So the exponent hasn't changed at all, but you'll see your values end up changing from the original, because basically every value that you had when you did the 2 to the x is going to be 3 less than it was originally, because you're going to compute that value. So the 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, and then you're going to subtract 3 from each. So in this case, instead of them being 1, it's going to become a negative 2. Instead of them being a 2, it's going to become a negative 1. So you'll see each value is decreasing by 3. So you can probably already guess what the graph is going to look like. If each value is decreasing by 3, then that means the graph is going to drop down those 3 units, right? So you can see, just take a look through and see where I've got the rest of the numbers there, but basically you can already kind of tell what's going to happen with the graph. So if you look at the graph, of course, it has actually dropped down 3 units. It's still the same shape again as before, but this time not only the y-intercept changed, because the y-intercept has changed again. It's now at negative 2. It was at 1 before, so of course we drop down 3, it becomes negative 2. But the asymptote has actually changed as well. So the line that it's kind of trying to go to but never reaching is now going to be at y is equal to 3, as opposed to being at y is equal to 0, so the x-axis. So both your asymptote and your y-intercept have changed in this case. And I haven't written this out for you yet. Most of these I've kind of got pre-made, but I'll just show you something very quickly because I think it might be helpful to you. If you think about the fact that in our quadratic, you had x minus plus k, and then in this one you have y is equal to, I'll show you what I'm doing in a second here, I'm just going to put an x and a k just to kind of, an h and a k just to kind of show you what's going on here. So if you remember in the quadratic formula, if you looked at the quadratic formula like this, to graph it, the regular one was just, of course, your x to the 2. But if you took anything and you subtracted it from your x value here, then that's going to alter your graph by moving it to the left or the right. The same thing here. So in the same way that you have your x minus h here, you could say that you have kind of an x minus h up in your exponent. So whatever you add or subtract to the exponent is going to cause that same kind of shift. It's going to cause your graph to move to the left or the right based on the original. And similarly with the k, when we talked about the k value before, if you add something onto that quadratic equation, it shifts your graph up or down. The same thing happens here. If you add something, and we'll call it k again, onto your equation for your exponential function, it shifts your graph up or down. So just show you the parallel there. It's basically the same kind of translations occurring with the exponential functions as did with the quadratic functions. So we will move on. That's basically just showing you some of the different ways that we can manipulate the exponential function graph, and like it says here in the notes, so based on whether the change is in the exponent, so it's happening to the exponent itself, or it's happening to the exponential function, you get different translations. You either get a left or right translation or an up or down translation. So the next thing that your book talks about is a little bit different, but it's very important. Equations where x and y are interchanged. So typically, if we're given an equation, it's y equals something x, and we're asked to plug in values for x, and then we get pairs, we get sets of coordinates, we get x and y values that are coordinates, we can plot them on a graph. In this case, it's the same type of principle, but instead of saying y equals something x, we're going to say x equals something y. So we're basically just kind of plugging in the variables backwards. We're still going to, when we plot them as x, y, because as we know, we always plot coordinates as x and y, but the way that we find our coordinates is going to be a little bit different. Instead of choosing x values and plugging them in, we're going to choose y values and plug them in. So for something, and this will be helpful to us to be able to work with graphs and manipulate graphs or equations of which the y and the x value have been interchanged. It's at this point you don't really overly see the relevance, but it's got some interesting parallels to point out. So we'll go through this example. So if you have x equals 2 to the y, like I said, this time you're not going to pick x values and plug them in, you're going to pick y values and plug them in. So we've gone ahead and done this here, and again, all of this is in your textbook. If you want to follow along, you can kind of just follow along with the textbook and read the things there. So if you've got your y is equal to 0, if you plug it into that equation, x equals 2 to the y, you're going to get x equals 2 to the 0, which is 1. If you have y equals 1, you're going to get x equals 2 to the 1, which is 2. If you have y equals 2, you're going to get x equals 2 to the 2, which is 4. So you'll see we're actually getting the same values here as we did before. We're getting our 1, our 2, our 4, our 8, our 1/2, our quarter, and our 1/8. They're the same values, but because we've flipped those x and y values, we're going to get a slightly different looking graph. So you'll see then if we make our chart, that kind of tells you which x values go with which y values. You'll see that now the y values are the ones that we typically have for the x, so the 0, the 1, the 2, the 3, the -1, the 2, -2, and -3. And then your x values have changed according to your y. So what you get is a graph that basically looks kind of like a weirdly flipped version of our original graph. So we still have a curve that's going up very quickly in one direction and coming very close to an axis in the other direction, except instead of coming closer to the x-axis this time, it's coming closer to the y-axis. And it's going up, basically up in this type of direction as opposed to going up to the left or up to the right. So if you look at it compared to a graph of the normal function, so something like y to the 2x as opposed to y is equal to 2 to the x as opposed to x is equal to 2 to the y, you'll see a very interesting kind of parallel between those two. So we have the same shape, but the graph has actually been flipped over the line y equals x. So the line y equals x would just be the one that kind of goes straight up diagonal through the middle. You'd have 1 is 1, 2 is 2, 3 is 3, so it would be a very straight diagonal line. So you'll see if you look at it, and I've drawn a picture to illustrate this for you, that the graph has literally been flipped over that y equals x line. However, you still get the same shape. So if you take a look at what I've drawn for you here, you can see very clearly that this one kind of goes up like this when y equals 2 to the x. And so this one kind of goes like this. So they're basically the exact same shape. They're just flipped across that diagonal y equals x line. And so you've got different asymptotes. This one will be y equals 0. This one will be x equals 0 for the asymptote. And this one will have a y-intercept of 1, and this one would have an x-intercept of 1. So obviously this one didn't have an x-intercept as it never reached x. This one then doesn't have a y-intercept, but it does then have an x-intercept. So they have the same intercept, it's just x versus y. And they have the same type of asymptote, it's just the x-axis versus the y-axis. So they're very similar graphs, just kind of flipped across that line. which is something interesting to note. So like we say here in the notes, basically it has the same shape, but its asymptote is now x is equal to 0, and the x-intercept is 0 and 1. There's no y-intercept, just as there was no x-intercept in the original graph. So, we're going to move on to the final topic in this chapter now, which is compound interest, applications of exponential functions. So now that we know a little bit about these functions, what can we do with them? What is their purpose? How can they help us kind of solve some practical, real-life type problems? So, we're going to talk about something called compound interest. So basically, when interest is paid on interest, that's known as compound interest. So it's the type of interest that's paid on an investment and a loan. So, for example, if you invested, and I'll show you my little graph here, if you invested $100,000, after 1 year, you're going to get the $100,000, and then you're also going to get 100,000 times 0.04 if that 100,000 is invested at 4% interest, right? Because we know 4% will be written as 0.04. So you're going to get your 100,000 back, plus you're going to get an increase of 100,000 times 0.04, which is going to give you 104,000. So what we're saying now, if you thought about it simply, then after 2 years, well, you'd get another 4,000 back if you just applied that interest to that first 100,000 you had. But because at the end of the first year you then have 104,000, you're not applying 4% interest in the second year to the 100,000. Now you're applying it to this larger number of 104,000. So you're going to get slightly more than 4,000 back in your second year. So overall, instead of just getting a simple 8,000, you're going to end up getting a number that's actually greater than 8,000 in terms of your interest, because you're getting interest not only on the original 100,000, but that 4,000 that you earned in the first year. That's what compound interest is, essentially. So I'll show you a little trick here. We say 100,000 plus 100,000 times 0.04 in order to get the interest, but there's a bit of a simpler way of doing it, and I'll show you. I wrote it out on the little paper. So if you have 100,000 plus 100,000 times 0.04, basically it's the same as saying you have 100,000 times 1, right? Plus 100,000 times 0.04, because you're getting 100,000 on its own, so times 1, and then 100,000 times your 0.04, which is that interest that you're getting. So if you write it out like that, 100,000 times 1 and 100,000 times 0.04, you can kind of factor out that value of 100,000. They both contain 100,000. So if you factor it out, you're left with 1. Oh, that's supposed to be a plus. Sorry. If you factor it out, you're left with 100,000 outside, and then you've got 1 plus 0.04 on the inside. So instead of saying 100,000 plus 100,000 times 0.04, you can actually write it as 100,000 times 1.04. So by timesing it by that 1, you're taking into account that you still have that 100,000 you started with. And then by timesing it by the 0.4, so adding it and timesing it by both at the same time, you're not only taking that 100,000 you started with, but you're also taking your interest and adding it on. So you end up getting the same value as you would when we did it like this, when we just added the 100,000 plus the 100,000 times 0.04. So it's just a lot easier to write it like that. Whenever you have an interest rate, if you're given a 5% interest rate, you multiply something by 1.05. If you're given, I do this for sales tax all the time. So if I know tax is 13% and something is $30, I will multiply the item. If we write 30% as a decimal, or 15% as a decimal, it would be 0.15. So instead you say 1.15, and you multiply that $30 by 1.15, and you automatically get the value with the tax included. You don't get the two values separately and have to add them, so it just kind of saves you an extra step there. So knowing what we know now about being able to just multiply it by 1.04 instead of taking the number and then adding 4% of it, I'll show you how we would then calculate the interest for the second year. So, like we said, if it's in the account for 1 year, you end up with 100,000 plus 100,000 times 0.04, or 100,000 times 1.04, as we just saw. So you end up with 104,000. If the amount remains in the account for a second year, and this is what I was talking about earlier, you get 104,000 plus 104,000 times 0.04. So you're not only keeping that original 104 that you for you gain in the first year, but you're also getting interest on top of that. So you end up getting basically 104,000 times 1.04 again. So it's multiplied by that interest rate again. Or if you want to say it another way, you could say it's 100,000 times 1.04 for the first year, then multiplied by another 1.04 for the second year. Which, of course, if we multiply by the same thing twice, is the same as saying 100,000 times 1.04 squared. So if you actually calculate that out, like I said, instead of just getting 108,000, which would be predicted if you said, well, I get 4% of 100,000 twice, you're actually going to be getting more than that. You're going to end up with 108,160, because you're not only gaining the extra 4,000 that you'd be gaining for interest on the second year on 100,000, you're also gaining an extra 160 in interest that you got on that 4,000 that you owned in the first year. And so when you compound interest like this, and it kind of, you end up getting compound on your interest each year, then that's what we call compounded annually. As we know, annually is something that happens once a year. And like I said, if you only had simple interest for 2 years, it would be the same as saying, well, I had 100,000 times the interest rate times 2, because we went for 2 years, so you'd only be getting 8,000, right? So if you only have simple interest, it's actually going to give you less than with the compound interest over a 2-year period, like I mentioned. So basically, like I said, when in the second year the interest is earned on the first year's interest, we say that it's compounded annually. And like I said, as you can see, after 2 years of compounded interest, you would end up getting a higher total payoff than you would with just simple interest. So for example 6 in your text, you can see this on page 871 there. Basically, it tells us the amount of money A that a principal P will grow after T years at interest rate R. I know this is very complicated with all the variables, but basically just saying that you have an amount of money that you're making, or the amount of money that you get overall, A, that a principal P, so principal is the initial amount you invest, will grow after T years, so T is the number of years, at interest rate R, so R is your interest rate, compounded annually, is given by the formula A is equal to P times 1 plus R all to the T. So if we're talking about investing 100,000 at 4% interest, which is what we were talking about in our original calculations just then, and compounding it annually, the very first thing they ask you to do, there's multiple steps to this equation, but you take this and it says find a function. So it wants you to find a function using this formula that you were given and plugging in those values for your principal amount, which is 100,000, and your 4% interest. So if you plug those in, instead of getting P, then you have 100,000 here, and you plug in for your R value. We know our interest rate is 4%, which is written as 0.04, so you plug it in there. So basically the function that you end up getting is 100,000 times 1.04 to the T. And if you think about it logically, this makes sense based on what we were just talking about, because after your first year, if you plug in a 1 here, you just get the 100,000 times the 1.04, but just like we saw when we just solved that initial equation, after the second year, it's basically like saying you get the 100,000 times 1.04 to the 2, because you've multiplied it by 1.04 twice. So the same function can be used for 3 years, 4 years, 5 years, and so on. So they ask you to find the amount after T equals 0, so at 0 years, which obviously is just going to be the 100,000, and you'd see that if you plugged it in, you get 0, which makes this 1, because anything to the 0 is 1. 1 times 100,000, 100,000. If you plug in a 4, well, you're going to get the amount that you'd have after 4 years. If you plug in an 8, you're going to get the amount you'd have after 8 years. You should be able to do that yourself, so I'm not going to go through that one. And then you can graph it. So basically you would graph it in the same way you graph any equation. If you have your A and your T as your two variables, then whatever's over here, we tend to kind of consider that our Y value. So you would plug T as you would graph T as your X value and A as your Y value, and you'd see that you'd get a very similar graph to what we were talking about before. You'd get the exponential graph, the exponential function graph, except instead of 2 now, so obviously when it was 2 it was a lot steeper. If it's 1.04, it's going to be going up much less quickly, as you can see if you look at this example 6 on page 871. So that should be relatively straightforward. I'm not going to go through the graphic of that one for you. So just a few last things to point out. If interest is compounded semi-annually, so every half year as opposed to every year, you would make even more money during a 2-year period. You can see your book, it talks about this on the bottom of page 871 there. But if you think about it logically, if you just said, put it in an account, you're going to get 4% interest, simple interest after 2 years, then like we said, you're basically just going to get your 0.4 times your 2, so you're going to get 8,000 after 2 years. If you get interest every year instead, then you're going to see an increase, because not only did you get the interest of the first year, after the second year you added interest on to that initial amount, so you're going to get more. So it follows that if you get interest every half year, well, after half a year, you're going to get some interest. After the full year, you're going to get interest on that initial amount. So instead of having $4,000 in interest after the first year, you actually end up with $4,040 because you gain interest on that initial amount of interest that you got. And then, of course, after a year and a half and then 2 years, you're actually going to end up with slightly more than you would have had even in the annual compound interest. So you end up with, instead of $8,160 in interest, you end up with $8,243.22 in interest. You actually get more interest, and that kind of makes sense. So from what we've learned about how these interest rates work and the difference between how often they're compounded and how many years that you let the interest gain, we've kind of learned about the relationships between those a little. So obviously the more often you compound it, the more interest you end up with in any given time period. We've created a formula called the compound interest formula. It can be used for any time length of compounding and any time length of investment. So if a principal P has been invested at interest rate R and it is compounded 9 times a year in T years, so in T amount of years, it will grow to an amount A given by A equals P times 1 plus R over N all to the N times T. So you not only have to put the N value in there in the brackets, you also have to put it into your exponent as well. So it's a bit of a complex formula, but as long as you plug in the numbers, basically just as given, if you're given, for example, 7, I'm not going to write it out for you, but I'll walk through it with you verbally. So if they invest $4,000 in an account paying 2 5/8% interest compounded quarterly, find the amount in the account after 2.5 years. So if it's compounded quarterly, then that means it's 4 times a year. So therefore, we know our N value, which is the amount times compounded a year, is going to be 4. So you're going to plug in your 4 wherever N is in that equation. We know that our interest rate is 2 5/8%. So you're going to plug that in where your R value is. Now that one is a little bit more complex to write as a decimal number, but you basically just take it and convert it into a decimal. And then your exponent there is going to be your amount of times it's compounded yearly, which is the 4 again, times the length of time it's been left in there for. So we know that if our T value is 2.5 years, and that's the same as saying 5 over 2 years, we convert it to an improper fraction. So 4 times 5 over 2 is going to give you 10 as your exponent. So hopefully you should be able to see how you basically, despite the fact that the equation looks very complicated, you're able to take those values and plug them into the equation. So I want you to try example 7 for yourself. I'm going to finish up the video now because that's all we're going to cover for today, but I will be giving you some questions from 12.1 for your assignment, so you can work on those in the next week, and then when I come next week we'll go through the test and we will continue on with chapter 12. So definitely take a look at this and try to figure out what's going on and try to work through some of the questions, and I will see you next week.